All right, good morning, everybody. And to echo Steve's sentiments, welcome to our Security Summit. It's really nice to see all of you here. Now, I'm not really going to talk about an open problem that we have per se, but what I will be doing is talking about how an academic idea makes its way into an industry product. Now, I'm very fortunate to be able to speak about this idea, but these people listed in the team section are really the people who are doing most of the hard work. So the top line there are the active engineers on the project, and the two individuals below helped us out while they were at Mozilla. Now, I'm going to start with a series of questions. They're not complicated questions, so don't panic. Who here uses the web on a daily basis? And who uses the web to conduct sensitive transactions? Online shopping? More than I would like. Online banking? Connecting with our nearest and dearest? But why do we trust it? Well, I would argue that we trust the web because we have TLS that works in combination with a public key infrastructure, a PKI. Now, I've spent a lot of time thinking about TLS, and I have the PhD battle scars to prove it, but I've sort of taken the PKI bit for granted. And as a browser vendor, Mozilla cares a lot about this PKI bit, and we should all care about this, because if there are problems here, it means that there are going to be problems for every single user on the web. Now, most of us in this room should be fairly comfortable with how the web PKI works. There are these things called digital certificates, and they bind an entity's identity to its public key, and they are issued by certification authorities. Now, right at the top of this chain, we have the root CA, and its certificate will be embedded in the browser. When we issue end entity certificates, there might be a number of intermediate certificates along the way, attaching the appropriate digital signatures as we go, and we build this chain of trust that eventually leads back to the root. And this is effectively how we inject trust into the web. But what if something goes wrong, right? It's estimated that over 500,000 private keys were compromised because of the Heartbleed vulnerability. Now, estimates vary, and it's actually probably a lot more than 500,000 private keys. And why do we care? What could happen? Well, an attacker could man in the middle your TLS connection and potentially decrypt your TLS session, the current session, or an attacker could effectively impersonate a server, which is bad. So what should happen when a private key gets compromised? Well, the owner of that private key should contact the CA and request revocation of the corresponding public key certificate. So then the CA needs to produce a public and cryptographically verifiable attestation that this certificate should no longer be trusted. And the responsibility lies with the client to check for revocation. So revocation is important, but revocation in the wild is broken. And what I'm going to say over the next 17 minutes or so is I'll talk about what current methods we have for revocation checking and why they don't really work in the browser ecosystem. I'll talk about a new way of doing things, CRLite, and this is an idea that was born in academia, and I think we have one of the authors with us today. And then I'm going to talk about how we're translating this idea for use in Firefox. And if there's time, I'd like to end talking about what it means for an industry idea to take root, or an academic idea to take root in industry, and whether or not initiatives like this are helping us to move towards a more robust PKI. All right, so what methods do we currently have for checking revocation status? There are certificate revocation lists, CRLs, and these are quite simply lists with serial numbers of certificates that have been revoked. They are produced by CAs and they are signed by CAs. A CA will embed a URL in a certificate it issues, and when a client sees this URL, the client has a responsibility for downloading the CRL and checking for revocation status. Now, we don't really like CRLs because they add a lot of latency to the connection. You have to download a big file, often multiple megabytes, before you can display a page. So we don't really use CRLs in Firefox. Then there's the Online Certificate Status Protocol, or OCSP. So this allows a client to request the revocation status of a single certificate. It sends an OCSP request to a CA's OCSP responder and receives the response. Now, in theory, this should be a little bit better, but it also adds latency to the connection. There's a privacy problem here because now the CA knows what the domains that the client is visiting, and these things often fail in practice. So we support this mechanism, we don't really like it. Now what you might notice in these two mechanisms is that the client is doing a lot of the work, right? But what if we shift all of this to the server? So what if instead the server does this whole OCSP dance and it staples the OCSP response to the certificate that it's going to issue, right? Now, this is a lot better. It helps with the privacy concerns. There's a reduction in latency, but it's not quite perfect because attackers can strip off this OCSP response. And in so doing, the attacker can happily fail open its way to victory. And what does that mean? Well, in the mechanisms that I've described, if a client cannot determine the revocation status of a certificate, it goes ahead with the connection anyway, even if in reality the certificate has been revoked. If it were to fail closed, the client would terminate the connection if it could not determine revocation status. And this is what happens in a mechanism called OCSP must staple. This is a TLS extension, signals to the client you will be receiving an OCSP response, and if the client doesn't receive that response, it tears down the connection. Now, we really like OCSP must stable because it checks a lot of the boxes. The problem is it's not very widely deployed on the web, right? And a lot of hosts don't really support OCSP stapling. So in all of the mechanisms that I've described that are deployed at scale, there are problems. There are delays. And in Firefox, we see additions of up to 200 milliseconds. And I actually think in some cases it's much more than that. They fail open, and there are privacy concerns. But what if we could push all revocation information to all of the clients? And there are already initiatives along these lines. There's Google's CRLate, and there's Mozilla's One CRL, which push partial revocation information to clients. Why not all revocation information? Well, I'll let you think about that for a second. And of course, there are some other ideas. One of them involves using FM radio to send revocation information to clients. So are all clients going to install FM receivers? Probably not. So the problem with pushing all revocation information to clients is, of course, size. Size matters. And this is where CRLite comes in. It compactly and efficiently stores revocation information and gets it to clients. And what is the size trick? How does it do this? Well, it uses cascading Bloom filters. And I'll talk about those in just a second. But with initiatives like certificate transparency and internet scans, we now have a pretty good view of the certificate ecosystem. So CRLite harnesses this data and compactly stores it in a data structure that supports queries to the finite set of unexpired certificates. Okay, Bloom filters. So what is a Bloom filter? It's a probabilistic data structure that allows for the insertion of arbitrary-sized data elements. So you need a bit vector or a bit array of size m, and you need k hash functions to determine array indices. So this is a very contrived example. It's for illustration purposes only. So how would we put data item d in the filter? Well, we'd compute h1 of d. This gives us 4. So we set the bit in array in index 4 to 1. We compute h2 of d, this gives us 11. We set this index to 1. We keep going, we set 9 to 1, and then we're going to set 2 to 1. Right, so now this item is in the Bloom filter. What if we were to put another data item into the Bloom filter? It might look something like this. And you might notice that there's a magenta bit somewhere there. And why is that? That's because two data items have collided on the same index. And this can definitely happen, and there are also multiple hash functions. Now, how do we determine if something is in the Bloom filter? Is D star in this filter? If any of the HI D star values is 0, then it's not in the filter. We know that. If all of these HI D star values are 1, then it might be in the filter. Right? So maybe it's a legitimate insertion, maybe it's not. So we're going to have false positives. Right? And this false positive rate is going to be determined by M, K, and the occupancy of this filter. So what we'd like to do is we'd like to harness these Bloom filters. We want to store the set of revoked certificates, R, in a Bloom filter, right? And here, U represents the set of finite or unexpired certificates. So if we were to store the set R in a Bloom filter, we're going to get false positives, right? But why don't we just store those false positives in another Bloom filter? right? So this is the idea of cascading bloom filters, and this is what CRLite harnesses. So CRLite does something like this. We take R, we put it into the first bloom filter. This is bloom filter number 1. But there are going to be false positives. And what are these? These are elements of S, so these are unexpired, unrevoked certificates that should not really be in this first bloom filter. So let's put those into another bloom filter, right? Again, we're going to have false positives. And what are these? These are elements of R that shouldn't really be in bloom filter number 2. So we keep going like this until there are no more false positives, and we get a number of different bloom filters. So what does this mean for data elements in these bloom filters? So if D star is not in the first bloom filter, then it's not in R. If it is in the first bloom filter, well, we don't really know because they're false positives. If it's in the first bloom filter but not in the second one, then it is in R. If it's in both of them, again, we don't really know. If it's in the next one, if it's in bloom filter 1, bloom filter 2, but not in bloom filter 3, we know it's not in R, right? If it's in all 3 of them for a 3-level bloom filter, then it is in R. So we want to use this structure, this data structure, to determine whether or not an unexpired certificate has been revoked. So we start I is equal to 1, and we look inside these bloom filters. And we keep going until U is not in a bloom filter. If I is odd, then it hasn't been revoked. It's not in R. If I is even, then it is in R. If it's in all of them, we look at the number of levels of bloom filters that we have. If it's odd, we know it is in R. If it's even, it's not in R. Right? So this is how we determine the revocation status of certificates by looking at this filter cascade. Now what we want, obviously, is the minimum size possible for this data structure. Now a bloom filter, singular, is minimized when K is set to this and M is set to this, or M is this. The question with cascading bloom filters is, well, how do we set P to get the minimum possible size? There's some really nice analysis in the paper, and it actually shows that it's optimal to set P1 for bloom filter 1, this is your biggest bloom filter, and to use a different false positive rate P for the remaining bloom filters. So we define P1 to be this. It depends on the size of R and the size of S, and also on the false positive rate P. And when P is 0.5, we get close to a theoretical lower bound for the size of this filter cascade. And there's some really nice simulations in the paper that confirm that this is actually true. And the good news is that the size of this thing is going to be dominated by R and not as S grows. S is usually much bigger than R, so we wouldn't want that to dominate the size of this. All right, now in terms of the CRLite architecture, there are 2 agents that you need to keep in mind. There's the client that needs to do the revocation checking, and there's the CRLite aggregator, which is responsible for constructing this filter cascade and getting this information to clients. Now, I have shamelessly stolen this diagram from the paper to represent the academic idea of what the architecture would look like. We start with raw information. This goes into the aggregator, and we validate and extract active certificates. Then we use CRLs and OCSP responses to construct R. We're going to put R into this cascaded bloom filter, and then the aggregator produces a daily filter, which in the papers are recorded at about 10 megabytes, and a delta update. So this is the difference between yesterday's filter and today's filter. So if you downloaded yesterday's filter, you don't need to download the whole thing again. You can just download this delta, which is quite a small file. The aggregator will also produce an audit log so that third parties can independently verify the construction of this cascade. And it's up to clients to go and fetch these files and do the revocation checking. Now, in the academic paper, it's stated that this idea is deployable today. So let's find out if that's true. For anyone who's a Def Leppard fan, you might notice that sort of my subtitle links to the title, but don't take it too seriously. Now, at Mozilla, we realized that using CRLite was going to help us to do things the Mozilla way. As part of our principles, we care about the privacy of users on the web, and we use OCSP, which isn't really great for privacy, and CRLite can help us there, and also the reduction in latency is going to be really nice. So I stole this slide, this little gray box, from one of the CRLite engineers when he was talking about why Mozilla wants to think about using CRLite. It has CRL-like properties. There are very small data sizes, means it will be fast to pass. The incremental update function was very appealing. It would scale well, and it could build on the useful properties of certificate transparency. Now, this is our architecture. So this is what we want to do, well, what we are prototyping in Firefox. So we are actually only using certificate transparency information. This is going into the aggregator. And we're also using CRLs only to construct our set R. Right? We construct our filter cascade, and we produce our daily filter file, and we produce 4 delta update files in a day. Right? This is what we want to do. And our files are quite small. We're at 5 megabytes and 0.3 megabytes for these files. And what's really lovely is that we already have the infrastructure to sign and push these files to our clients because of the one CRL mechanism that we have. Now, the paper did include a prototype, and it was built as a Firefox extension. And because it was built as a Firefox extension, the authors had to rely on TLS APIs for checking of certificate chains. And this is JavaScript, not really the most performant of languages. We don't have to build it as an extension. We can make it native to the browser, so we can put it inside Firefox, and we can use languages C++, we use Rust. We use a little bit of JavaScript, but mostly it's in C++ and Rust. Now, in the academic prototype, they record 10 milliseconds for checking a certificate chain. Right? And this includes the passing of certificates because the API provides unpassed certificates. So these are a few numbers on our side that I got from one of our engineers about a month ago maybe. And for us to check a certificate is between 0.01 and 0.04 milliseconds. But I will qualify that we're checking end entity certificates, and we still make use of our one CRL mechanism to check for the revocation of intermediate certificates. Now, what has it been like to take an academic idea and put it into an industry product? The idea tracked well with us. We really liked it. And the fact that there was a Firefox prototype really helped. But the paper didn't, or really couldn't, take our existing infrastructure into account. Now, in our case, our existing infrastructure has been a bonus. It helps us. But this isn't necessarily always going to be true for other initiatives. Early on, we had some contact with the authors, more contact, and then as we progressed with the project, we weren't that in touch with the authors or what they had done, and maybe we could have sustained that throughout the project. And I will say the timing is right for this type of solution to exist because of other initiatives that have come to the fore, like certificate transparency. So these tools can all work together to give us a solution like CRLite. Now, when I spoke to one of the CRLite engineers, I said, what do you think about this system? What do you think about this process? And he said to me, it's an excellent solution to a problem we just shouldn't have. And this is interesting, and he's right, because we have OCSP must staple, right? We could use this, but it's not widely deployed. And the reasons for it not being widely deployed, I think, go beyond engineering, and it's a can of worms I won't open right now. Okay, so I started the day with a question, or a series of questions. I'm going to end with one. Do we think that initiatives like this, or CRLite in particular, is going to help us move towards a more robust web PKI? I definitely think that is going to help. And I can only really speak from being in the tech industry, but after being in industry and then doing a PhD and then doing back in industry, I can see the importance of the influence that these two spheres have on each other and the importance of the relationship between academia and industry. And I really do believe that they are friends. So, thank you.